All right, so we are at section 2.33 where we're talking about Bayes' theorem for Gaussian variables. So the idea is that we're going to be given a marginal distribution or a prior distribution that's Gaussian and a likelihood that's Gaussian, and then we're going to be interested in the marginal distribution on one of the variables and also the posterior distribution. So that's kind of where Bayes' theorem comes in. And it's going to, again, give us some more practice about using completing the square. We're going to be using some of the results we used in the first couple of sections on marginal and conditional expressions. So if you haven't watched those videos or read those sections, now is a good time to do that. And then we'll just get a couple of expressions that we're going to be using in subsequent chapters when we start working with specific types of models. So what I'll do here is we'll go through the material in the section, and it's again just a lot of algebra. It's not very complicated, and we'll arrive at the expressions that we're aiming at. But then I will try to give you a little bit of intuition about maybe where those expressions come from, kind of maybe deriving them in a simpler way, or trying to understand them in a maybe in a slightly more intuitive way, so that it's not just expressions for you. But at the end of the day, we'll just arrive at a couple of expressions, which you can just understand how they were derived, but don't worry too much about memorizing them. You'll get plenty of chances to do that later on when we're using them all the time. Okay, good. Okay, so let's start. So in the previous two sections, so hopefully you've seen the videos on those. We considered a Gaussian p of x in which we partition the vector x into two subvectors x of a and x of b. And then we found expressions for the conditional distribution. We're going to use that one today. And the marginal distributions. So we're going to be using those properties today. And we noted that the mean of the conditional distribution was a linear function of x of b. So there was this nice idea of you're given some properties of x of b, and then the update is, you can view it as an update to x of a given x of b. And this was a linear function. So now we're going to be looking at a related situation. We're given a Gaussian marginal distribution p of x. You can again think of that as kind of a prior distribution on x, and a Gaussian conditional distribution y given x. So this is kind of where your evidence is coming from. So you have a prior distribution, you have some evidence, some observations y, in which, and this is the important bit, in which py of x has a mean that is a linear function of x and a covariance which is independent of x. So these two properties are going to be really important. So the results here are for this specific case. And this is an example of a linear Gaussian model, which we'll study in 8.14. So the idea is we're just going to be deriving some of the results that we're going to need later here because we've got the machinery to do it, and it just gives us a chance to apply that machinery and get some of these useful results. Okay, so what are we after? We're after the marginal distribution on y and the conditional distribution p of x given y. So again, let's just see what those would be. So if we're given p of x and p of y given x. And so we want p of y, which is going to equal p of y given x times p of x dx. And we're not going to evaluate this integral directly. We're just going to look at, use our completing the square tricks, and knowing the fact that it's going to be Gaussian, we'll see that it's Gaussian, to just come up with this mean and variance. So we don't actually do any integrals. And then we also want this posterior distribution on y, which is going to be equal to py given x, p of x over p of y. But again, we're not going to be deriving, we're not going to be applying that expression directly. We'll just we're going to actually use one of the expressions we found previously to just plug in the values and get the answers. Okay, so let's look at what we've got. So we've got a marginal distribution, which we've got, which we said was Gaussian. One thing to notice, of course, is that we're going to be working with precisions. So the covariance here is going to be and that's what that is. And now here is where our linear model comes in. And actually, if you want to get technical about it, it's not actually linear. It's something more general, which is affine. So this ax plus b is not a linear function of x, and that's because for linear functions, they have to satisfy, let's say, a of x plus a of z for a linear function, it's going to be a of x plus a of z, right? So this is going to be the sum of the two linear parts. But for this function, a of sorry, let me just make it more clear. So for a linear function, so f of x plus y is supposed to equal to f of x plus f of y. That's one of the properties of a linear function. Now, if our function is f, let's say f of x is equal to a of x, then everything is fine, right? Because f of x plus y is going to equal to a of x plus y is equal to a of x plus a of y, which is just the sum of those twos, right? So that's fine. But what we have, we don't actually have that. We have something more general. It's a linear function plus an offset. And that actually is not, the result is not linear. Well, it's only linear if that offset is 0. And you'll see why that is. So let's say f of x is equal to ax plus b. So we just defined it as that. Well, f of x plus y is a of x plus b plus a, sorry, it's going to be a of x plus y plus b, right? Which is going to be ax plus b plus ay, which we can write this as plus b minus 1, which is f of x plus f of y minus b. So f of x plus y will only equal to f of x plus f of y if b is equal to 0. So in general, it's actually not a linear function. It's a affine function. So this, this result that we're going to be talking about is going to apply to these affine relationships as well. So let me just put the colors back here and erase that. Great. So let's just make a note that this is actually affine. So this is a generalization of linear functions. So this will also work for the linear case, but the properties we're going to be talking about here will work for affine relationships relating y and x. Okay, so here we're saying that given x, the mean of y is an affine function of x. So it's a of x plus b, and it has some precision. So we're given this, and now we're going to be interested in figuring out what the marginal distribution of p of y is and what the posterior distribution is on x given y. Now a couple of things to notice. So a doesn't have to be square, right? So so if x has dimensionality, y, and that's just reflecting the fact that the dimensionality of your observations. So again, you can think about x is some vector and it's producing some set of observations y, and now x could be, for example, it could be I don't know. Imagine it could produce much higher dimensional extrinsic. I don't want to use this terminology, but what is, for example, let's consider maybe I'm going to make this example up, but let's suppose you had the digits 1 to 9, and your observations were, so you had the digits 1 to 9, and your observations of these were like pixels of the images 1 to 9. So you would have the picture 1, and you would split this up, and this would have, so now you would have this essentially discrete values for x mapping to a million dimensional observations, right? Because you'll have a 1,000 by 1,000 image of the number 1, and then a 1,000 by 1,000 image of the number 2, and maybe corrupted by noise, and you're trying to figure out which digit it was. So that's a situation where let's say this would be, you could think of that as being putting it on a one-dimensional on a line, being so maybe one dimension mapping onto a million dimensions. So there's no necessity that the dimensions of x has to equal to the dimension of y. You could have another an easier example is, imagine you have your observations are just a subset of the values. So let's say, I don't know, again, you have I'm just making this up, but let's say your latents are the values of these, these x's are the values of these grid points, and now you observe only a subset of them. So now you've projected down. You've gone from, let's say 1,000,000 dimensions to 1,000 dimensions, and now you're trying to figure out, what those 1,000,000 dimensions were, the values of those 1,000,000 dimensions were. So anyway, this is just trying to tell you there doesn't need to be, so dim x does not necessarily equal to dim y. And so that means that this a that takes you from x to y is not going to be square. It could, in general. So it says if x has, if x has dimensionality m and y has dimensionality d, then the matrix A has a size d times m, right? Because the m talking to x and the d producing the y as the output. Okay, so now what we're going to do is we're going to look at the joint distribution of x and y. And so the first thing we're going to do is we're going to pack x and y into this variable z. And what we're going to look at is the log of p of z. And so the question is, well, why are we doing that? And again, this is just because we're kind of going to be guessing that it's Gaussian. And so, if you have a Gaussian distribution, so, p of z is going to be equal to some 1 over something times exponent of 1 minus 1/2 of z transpose minus 1z. So if we take the log of this, and assuming everything is Gaussian, then, and I forgot the mean term. So basically what we're going to care about is what's inside this exponential. So the log of p of z is going to equal to some constants that don't depend on z minus 1/2 z transpose, in the case where if z has 0 mean, which it doesn't. But so all we care about is this stuff. So that's what we consider the log of the joint distribution. So how are we going to do that? Well, we're going to, and what is the joint distribution? So the joint distribution is, p of x is going to be p of x times p of y given x. So we're actually going to, and so then the log, and this is like p of z. P of z is going to equal to ln, exactly as he's written, so I don't need to repeat it, ln of p of x plus ln of py given x. And so we just literally write down the corresponding equations for this and the corresponding equation for that. So you see y minus the mean times the precision plus some constant terms that don't depend on x and y. And now what we're going to do is we're going to group these by x, the x and the y. So we're going to first collect the terms that are x by x, then the y by, and actually the very first thing we're going to do, so let me back up. So we're going to first we're going to try to figure out what the covariance is, or what the precision is actually. And you'll remember that, so what's our strategy going to be? Well, the strategy is, the idea is that inside that, inside that expression, of z minus mu transpose, let's call this whatever, I think it's r times z minus mu. So when we take the logarithm, what you're going to end up getting is z trans. We want to first figure out what this precision is. So we're going to just try to isolate the quadratic term. As before, we've been doing this the whole time, in the other section as well. And now we're going to say, okay, well, we're going to partition this now. So this is going to equal to, remember, x, y transpose r times x, y. And then we can write this as, so this is, again, x, y transpose. And let's call this rxx, rxy, ryx, and ryy. And this will be the this will be symmetric, so this will be the transpose of that. And now, so you'll notice that the reason why I've indexed them the way I have is because you'll end up getting an expression like that. So x transpose rxx plus x transpose rxy times y plus, y transpose ryx times x plus y transpose ryy times y. So if we just look at the quadratic terms in this expansion and just find the terms that are multiplying, have x on both sides, x transpose and y on one side, vice versa, and then y transpose y, then that's gonna give us all of these terms that we need from the precision. So that's exactly what we're gonna do here. So let's zoom back out. So so we consider, and maybe I should highlight this, we consider the second order terms in this thing. And now look, we're going to partition them out. So here's an x term, here's a y term, y x, and an x y. And so now, just for the exact same reason I just told you, so now let's this guy is just going to go over here because that is the r, that's the rxx term. Whereas y and y, so let's use a different color. So now L is going to go over here because that's going to be what's going to be multiplying the two y's together. And then x. So let's say where's the one with A transpose L? That's where that is, and so on. So that's where all those pieces come from, and that gives us R, which is the precision of our joint distribution. So we just literally oops. So now we just literally just take that, and that's just our precision. So we essentially just read it off. One thing too that he says is he always says that yeah. So this is again, this is kind of a technical point. It almost never comes up. You almost never have to worry about this, but we see that this is a quadratic function of the components of z. Hence, p of z is a Gaussian. It's not enough for it to be a quadratic. It's important that your precision matrix, this thing, is positive positive definite. So you need it to have all positive eigenvalues, and these ones will have all positive eigenvalues. But in general, like if you're just working with some quadratic function of of your variables, it's not guaranteed that it's Gaussian. So you actually have to show that these precisions you're coming up with, that they're all positive definite, that they all have positive eigenvalues. So that's just something to keep in mind. So just because it's quadratic doesn't necessarily mean that the result is going to be Gaussian. In almost every setting I've worked with it, they have ended up being positive definite, and you can almost always show that it is, but just keep that in mind. Okay. Yeah, the covariance matrix is found by taking the inverse of the precision, which can be done. We've done this before, so you essentially you just invert this and you get the covariance. So that gives us the covariance of this joint variable that we're interested in. Okay, great. And now again, we're just kind of playing the same game. So we can find the mean. Remember, again, going back to completing the square, and we found that if we complete the square, you've got z plus z transpose sigma minus 1 mu. Right? So again, we're looking at, so what we do now is we look at the linear terms. So now we're going to be focusing on the linear terms. We've already got our, do we call it R? Yeah. So this is, you can write this as z transpose rz plus z transpose r mu. Okay, so we've already used this part to figure out what z is, and now we're going to look at the linear terms in z. And so again, those terms are the ones where they only have, an x or a y, but they don't have x multiplying y's. And what we're going to do is we're going to pack this up into an expression. So this is this thing. This is z transpose. So we've got this, and it looks like it's going to be multiplying this term. And now let's call this b. And now we're interested in mu. So what we have is that b here is equal to r mu. So therefore mu is equal to r minus 1b, which is what we have down here. And making use of what our expression for r minus 1, we end up with this expression. Okay, so that's pretty cool. So now we've got, that gives us the mean, and it gives us the covariance. We just figured out what the covariance is. So we now have the results for the joint distribution, and then we can go back to what we found out in earlier sections on how to get the mean and variance covariance of the marginal distribution. And remember that for the marginal distributions of one of those components, it was actually really, really simple, right? So we found before that if we have x and y, and let's say the expectation of x and y is equal to mu of a and mu of b, and then the covariance of, you know, x and y was equal to, remember we had something like sigma xx, sigma xy, sigma yy. We found there that with this intuitive result that when you have the mean and the covariance of the joint distributions, then the mean and the covariance, the marginal distributions, are just found by reading off the corresponding elements. And that's exactly what we're going to do here. So we find an expression for the marginal. Recall that the marginal over a subset of the components of the Gaussian random vector takes a particularly simple form when expressed in terms of the partition covariance matrix. Okay. Specifically, its mean and the covariance are given by so and so, which is the expression I've just given you. So essentially, what we do is we look at y. Well, y is going to be, remember, this is so this was x and this is y. So we just read off the mean there, and the covariance is just going to be this bottom component of the covariance, which we found out was going to equal to that. So that's exactly what that is. So we found the joint distribution, and then we've just read off the corresponding corners to get the marginal results. This a special case, and so he says the special case is when a is equal to 1, in which case it reduces the convolution of two Gaussians, for which we see that the mean of the convolution is the sum of the mean of the two Gaussians, and the covariance is the sum of their covariances. So essentially he's saying that this convolution case he's talking about is, I mean, I think it's generally called the convolution. It isn't just, it's just a special case, but essentially the idea is that suppose you have p of you know, x is, you know, some Gaussian, and then p of y given x is just a plus I don't know, let's just call it rho squared or something like that. So the idea is this convolution is that and now you want to see what the joint distribution of y is, and this is just a general, but the idea is that what you do is for each point in x you just put, you know, you have a kind of a Gaussian on it, and now you have lots of points in x, and the distribution of the points in x is itself a Gaussian. So you essentially smear this Gaussian, you smear p of x with little Gaussians that that have the variances corresponding to rho squared, and the result there is that the result he's referring to is that then the mean of the resulting kind of smearing will be the sum of the means, and the variance will be the sum of the variances. So I think that's all he's talking about there. One thing I wanted to point out is that I think it was useful to kind of derive the result the way we have. You can derive it. I mean, you can kind of derive it in a slightly simpler way if you wanted to, and I think it's kind of useful. If you assume you know that the result is going to be Gaussian, because so it's just a kind of simple relationship. So we have that y is equal to a of x plus b plus some noise that has we're given that has, there is a noise. The noise has precision L minus plus noise of L minus 1. Okay, so now you can just derive these results in a very simple way. You can say, well, what is the expectation of y? Well, that's going to be the expectation of a of x plus b, because the noise is we're going to assume it's zero mean Gaussian noise. It's zero mean noise, basically. And so, well, what is this? Well, this is just going to equal to e times the expectation of x plus b, which is a mu plus b. So that's that term. And now what's the covariance of y? Well, the covariance of y is the covariance of ax plus b plus L minus 1, because we're going to assume that the noise on L minus 1 is independent of the noise on x. And from the way covariances work, we just know that this is going to equal to the covariance a times the covariance of x times a transpose plus L minus 1, which is a times, we're given that the covariance of x is lambda minus 1, a transpose plus L minus 1, which is this expression here. So that's just kind of one way you could just arrive at the result in a much faster way. But again, you have to show that this doesn't tell you that the result is Gaussian. So that's something you actually have to show. Whereas in what we've done, we've actually shown that it is Gaussian because we had a quadratic expression. And also, I think it was just good practice to see how to pack up these terms and how to kind of derive these results directly. Okay, and the last little bit he's going to do is an expression for the conditional p of x given y, and all he's going to do is he's just going to pull out the expression that we derived before. So in previous sections, we had a joint distribution of p of x and p of x given y, and then we figured out what these expectations were in terms of the means and variances there. So all he's going to do is just plug those things in. So we see an expression for the conditional p of x given y. Recall the results are most easily expressed, blah, blah, blah. We see that the conditional expression has a mean and covariance given by these, slightly kind of mysterious formulas. And in a second, I will try to give you some intuition from where they come from. And it's just something I kind of thought about today. As it's a way of, maybe kind of giving you a sense of where they come from. The evaluation of this conditional can be seen as an example of Bayes' theorem. So we can interpret the distribution Px as a prior distribution. So let's highlight that. If the variable y is observed, then the conditional distribution represents the corresponding posterior distribution over x. Right? Having found the marginal conditional distributions, we effectively express the joint distribution in the form p of x given y times p of y. Okay. And these results are summarized below. So here are some formulas. I think it's just good to be able to refer to this page later when we work with linear Gaussian models. You're just going to want to know where these come from. So I thought I'd just kind of wrap up with, I've already told you how you can kind of easily derive this one. Now this one's a little bit mysterious. So how can we kind of think about that? Okay, so yeah, so what I just wanted to do was, instead of just leaving you with the formulas for this for the posterior distribution, I was thinking today about how one could understand where this formula comes from rather than just taking it as granted, and I thought I'd share it with you. And the basic idea is to think about it as combining information from two sources, combining information about x from two sources. We have a prior distribution, which is this one, and then we have essentially another distribution on x, or more information about x that's coming through our observations. And the idea is that when in situations like that, in very simple situations like that, what you generally want to do to figure out what the posterior is you want to combine the information from the two sources, but scaled do a weighted combination that's scaled by the precision. So the source that has the highest precision, you want to kind of weight that more. And it makes perfect sense, right? And basically that's what this expression here is. You have a weighted combination of two sources of information about x, which is giving you a weighted, the weighted mean, and then the resulting covariance. So let's just see kind of, hopefully this helps. I don't know if this is kind of useful, but I just want to give you a little bit of intuition for it. So let's again, suppose we're in a situation where we have x and we observe y. And now this is going to be, we're given, x it has some just prior distribution. And let's actually work with the precision. So I'm going to call this, and these can all be just scalar variables. I'll just call it mu. So mu here is a precision. We're going to be working in precision terms. And now we're given that n of y given x. This is going to be the mean of y given x is going to be again x. And it's going to have its own precision rho. And now we're interested in p of x given y. And it will turn out that this is actually going to equal to a normal distribution. So it'll be useful to use the kind of symmetry of the exponential and that quadratic term to actually write this as, this is the same. If you actually write it out, you'll see that's the same thing. And that will turn out, so sorry, and the reason I do that is because to kind of show you that we're getting we can think of this as getting two sources of information about x. One says the mean is mu and the precision is lambda. The other one says the mean is y and the precision is rho. And you can imagine, so if your observation was, had very high precision, you would be dominated by the observation. Whereas if the precision of the observation was low, you would tend more towards the prior. And indeed, the posterior distribution in that case is going to equal x. And so now the mean is going to be mu times its precision plus plus x, plus y, so our observation, times its precision. And now we have a weighted combination, right? So you see, this is a sum of the precision. So you can think of this as there's one weighting, and that's going to be between 0 and 1, and another weighting that's going to be between 0 and 1. And the higher one of the precisions is relative to the other one, the more it's going to dominate the mean. And the precision of the result is going to be rho plus lambda. Okay, so if we can get things in this particular form, then we have a very intuitive result of what the posterior will be. And in fact, that is kind of what we have, and it kind of generalizes quite well. So we can kind of think of this as basically the same thing. The only complication is that we don't have, here x and y was just, x, y had the same mean. The mean of y was x, whereas here the mean of y is a of x plus b. So we have to kind of massage it a little bit to get it into the form that we want, which is like this, where they're kind of where we have kind of a distribution on x, basically. So all we do is, so let's just do the same thing. So I'm just going to copy this. So here is that. Okay, so let's just bring it down here. Okay. So again, we've got x, and this is going to be normally distributed. We just see that. But now, yeah, so we're going to stick with our precisions there. And now we're given observations y. And now we're told that this is kind of some complicated thing. Plus b, and it has some precision L. So notice I'm using precisions, not covariances. Okay, so to be able to apply this stuff, I need to actually write this as an expression as a Gaussian relative to x, not of y. So all I'm going to do is I'm going to just again use looking at the quadratic form that shows up. So if we actually write this out, we'll see that this is equal to, proportional to, we're going to ignore the normalizing constants and things. The exponential of minus y minus b minus ax transpose L y minus b minus ax. Okay, and so now we're just going to look at the same trick we've been doing before. Look at the quadratic terms in x. And so, if we look at this, is going to equal to minus 1/2 of x transpose a transpose L a x x. So this is going to give us, so this is going to be the precision for x. And then we want the linear terms. So this is going to be x transpose a transpose, and the bits that's going to come in is going to be this y minus b. Okay, so now we know this is going to be equal to, let's call the mean is going to be r times nu. So nu is going to be the mean of our distributions. So we want to write this as being being proportional to x with some mean nu and some precision r. Well, we've actually found r, and now we found what r nu is. That's right. So nu is going to equal to r minus 1 times a transpose y minus b. Okay, so now we've got that. So now we're basically in the same form as we were here, right? So we have x, we have some mean, the mean of x, and we have its precision. So now we can actually just, with some squinting, just apply our our heuristic from above. So we just say, look, P of x given y is going to be this combination, right? So it's going to be x, and the mean is going to be the precision-weighted means of the two parts, the prior and the likelihood. So we're going to have, what is the precision of the prior is, so it's something like that, plus r times nu, right? And that's exactly what we have here, right? With precision equal to mu plus lambda plus r. Well, what is this? This is just plus A transpose y minus b. Sorry, I forgot something. I was like, where'd the L go? It should actually be L times y minus b. There we go, much better. Okay. Over, and then there is a precision. So now, of course, there are, what does over mean when you have matrices? So that's where you actually have to go and work out that this is actually going to be on a left multiplication. So we're going to get minus 1 times and our precision is going to be that. And if we look, if we look back up at the expression that we have, let's just copy it down. Let's bring it all the way down here. Yeah, there it is, right? So that's exactly what we have. So we've got, and so here he's looking at the covariance, which is that minus 1. So what we've got this precision. So this is the covariance multiplying A transpose L y minus b times lambda mu. And the covariance is this thing to the minus 1, which is, let's just bring it all the way down, which is exactly what we have, right? So there is our mu, and we just found that r was equal to ATLA. So this is just r. So this is going to equal to, so basically, yeah, so I don't know how helpful that was, but the point of it is that this expression, you can actually think of it as you're combining information from two sources, the prior, and it makes sense, right? Coming from the prior and from the likelihoods, and you just express those in terms of x, and then you're back in the situation of doing the precision-weighted mean and adding up the precisions, which is where that expression, which is where these expressions come from. So hopefully that was helpful, kind of took some of the mystery out of those expressions, and yeah, maybe kind of gave you a new perspective for looking at those results. But again, as I said, you don't need to memorize these things, just know where they are, know how they're derived, and later on you'll get plenty of practice using them. So yeah, so I think with that, I think that's all I wanted to say, and let's hope to see you in the next video where we'll be talking about maximum likelihood for the Gaussian. So hope to see you there. Bye.